In this particular example, we've been asked to graph the quartic function y equals x to the 4 minus 8x cubed plus 20x squared minus 16x. One thing I should stress that when I ask you to do a curve sketching question, I expect that you show all the steps. I realize that most of you guys have graphics calculators and you can quickly ascertain certain solutions to the question without doing any sort of work. Therefore, I'm requiring that you show all your work just to ensure that you're not relying on the calculator. First thing we have to do is state the domain. Since this is a fourth degree polynomial, you should already be aware that there should be no restriction in the domain. Therefore, my x values go from negative infinity to infinity. The next thing you're asked to do is find the intercepts. Well, the y-intercept is found by setting x equal to 0. So you set x equal to 0 and solve for y, and you get a value of 0. So we know the y-intercept is 0, 0. That also happens to be one of the potential x-intercepts. Now, the other x-intercepts could be found, but it's a fairly long and cumbersome process, and so we're going to bypass that at this time. The next thing we have to do is determine if the function is even, odd, or neither. If it is even, then the f of x should be equal to the f of negative x. So I started by finding the f of negative x. That means everywhere in the function there was an x, I replace it with a negative x and evaluate that expression. And I find that f of negative x is equal to x to the 4 plus 8x cubed plus 20x squared plus 16x. You can see that this is not equal to f of x, because f of x was x to the 4th minus 8x cubed plus 20x squared minus 16x. So since f of x does not equal f of negative x, it is not even. Well, then we have to check if it's odd. To be odd, f of x has to equal negative f of negative x. So I merely take the answer for f of negative x that I previously worked out and multiply everything by negative 1 so that I obtain negative f of negative x. And I find that negative f of negative x is equal to negative x to the 4 minus 8x cubed minus 20x squared minus 16x. This is not equal to f of x. Therefore, the function is not odd. The next thing we have to consider if there are any asymptotes. This is a polynomial function, and polynomial functions don't have asymptotes. On the next screen, we've started by taking the derivative of our quartic function, and the resulting derivative is a cubic expression. We're taking the derivative because we are trying to find the maxima and minima for this particular function, and that's found by taking the derivative and setting it equal to 0, which is what we've done. I've then noticed that everything is divisible by 4, so 0 is equal to x cubed minus 6x squared plus 10x minus 4. Now, this particular cubic equation must be solved. Unfortunately, it can't be factored. So, therefore, we're going to rely on our rational root theorem. And we start by looking at the ratio of a0 to an, which is a negative 4 divided by a positive 1. So our possible rational roots are plus or minus 1 divided by 1, plus or minus 2 divided by 1, and plus or minus 4 divided by 1. We find that p of 2 is equal to 0, so therefore, using synthetic division, we can find the other factor for this particular cubic expression. So we've done our synthetic division, and we've ended up with 1, negative 4, 2, and 0. If you remember, the 0 is the remainder, and if this is indeed, if 2 indeed is a root of this cubic expression, then the remainder after doing synthetic division should be 0, and that's the case here. So, based on this, we can now conclude that our cubic equation, which is 0 equals x cubed minus 6x squared plus 10x minus 4, can be factored such that it can be expressed as 0 equals x minus 2 times x squared minus 4x plus 2. Well, the roots to that are going to be x equals 2, and using your quadratic formula, you would find that when you solve that quadratic expression, x squared minus 4x plus 2, you end up with an x value of 3.41 and 0.59. Those are approximations. Now, these are going to be the maxima and minima for this particular function. We still need to know their corresponding y coordinates. So we take those x values and we substitute them back into our original quartic equation. And we find that when x is equal to 2, y is equal to 0. So actually that particular extrema is not only an extrema, but it's also one of the x-intercepts for the function. When x is equal to 3.41, my corresponding y is negative 4. When my x value is 0.59, my corresponding y coordinate is negative 4 also. So we now have our extrema for the function. The next thing we have to do is decide where the function is increasing or decreasing. Well, a function is increasing when its first derivative is positive, and it's decreasing when its first derivative is negative. Therefore, what we're going to do is test the regions between the three extrema that we found previously on the last screen. So if you've noticed, I've written down a number line and put those three values of x, 0.59, 2, and 3.41 on that number line. And I'm going to test y prime, our first derivative, at values in the four regions created. Now I've chosen the x values 0, 1, 3, and 4. You may choose slightly different values if you so choose. What I find is that when x is equal to 0, the first derivative is equal to negative 16. So I put a little negative sign on my number line to indicate that all values of x in that region would produce negative values for the first derivative. Test the next region. So I chose an x value of 1. I find the corresponding value for y prime is 4. So I put a positive on that region of the number line. When x is 3, my first derivative is negative 4. Put a negative in that region of the number line. And when x is equal to 4, my first derivative is a positive 16, indicating that all values of x in that region generate positive solutions. So now I can conclude where the function is increasing and where it is decreasing by looking at this number line, remembering that it's increasing when my first derivative is positive. Therefore, it is increasing when my x values go from 0.59 to 2 in union with 3.41 to infinity, and the function is decreasing when my x values go from negative infinity to 0.59 in union with 2 to 3.41. The next thing I have to do is determine if I have any points of inflection. And if you remember, points of inflection are where a function changes in concavity. We use the second derivative to determine points of inflection. We must set that second derivative equal to 0. Or in some cases find where the second derivative is undefined, which is not going to be the case with this particular polynomial function. So we've taken our second derivative, y double prime, and we have 12x squared minus 48x plus 40. We set it equal to 0, and what we notice is that everything is divisible by 4. So 0 is equal to 3x squared minus 12x plus 10. We solve this quadratic equation using our quadratic formula, and we obtain 1.18 and 2.82. Remember, these are the x coordinates for my points of inflection, but I need the corresponding y coordinates. So I substitute these x values back into our original quartic equation, or fourth degree polynomial, and I find that when x is equal to 1.18, my corresponding y is -2.24. When x is equal to 2.82, my corresponding y coordinate is -2.24. Now, we're really not sure if those values are indeed points of inflection, because remember, with points of inflection, concavity must change across those points. So what we need to still do is test the second derivative in the three regions that are produced between those points that we previously calculated. So I write down a number line, or place down a number line. I put on the two x values that I worked out on the previous screen, 1.18 and 2.82, and now I'm going to test the three regions created by those two values of x on our number line. So I've chosen the x values 0, 2, and 3, but you can choose whatever values you want as long as there's a value representing each of those three intervals. So when x is equal to 0, my corresponding value for y double prime is 40. So I put a positive on that interval on the number line. When x is equal to 2, my corresponding value for y double prime is -8, and a negative value is placed on that interval on the number line. And when x is equal to 3, my corresponding value for y double prime is 4, and I put a positive value down on that region of the number line. Remembering that the second derivative helps us to understand where a function is concave upwards or concave downwards, we can now conclude that the function is concave upwards in the regions from -infinity to 1.18 in union with the region from 2.82 to infinity. Remember, functions are concave upwards when the second derivative is positive. Concave downwards, the second derivative must be negative. Therefore, for this particular function, it is concave downwards for x values between 1.18 and 2.82. On the last screen, we've taken all the information from the previous four screens and we've put it together to draw the curve, in this case, of our quartic function. I should mention that normally I wouldn't do this as the very last step. I would actually have my coordinate system drawn on a separate piece of paper, and as I work out each particular important piece of information, I would plot that information as I go. A lot of times it's easy to catch your mistakes if you do it in that fashion, opposed to collecting all the information and then plotting it at the end. The only reason I've done it this way is that I just couldn't fit everything on one screen. Well, I've drawn my Cartesian coordinate system, placed a scale on both my horizontal and vertical axes. First thing I've plotted is the y-intercept for my function, which I know to be 0, 0. The next thing I've plotted are the maxima and minima that I had previously calculated using the first derivative. I knew that one of my maxima was at 2, 0, so that one's plotted. Another maxima minima is going to be at 3.41 and -4. And then the last one, the last extrema, is at 0.59 and -4. I've put little square green squares around those to signify that those are the extrema that I previously calculated. Now, we did talk about the increasing and decreasing intervals, but I'm going to look at that just in a few minutes. Right now, I'd like to plot my points of inflection. So my points of inflection were found by using my second derivative and setting it equal to 0, and we found them to be at 1.18 and -2.24. Those were the x and y coordinates, so that's been plotted. The other point of inflection is at 2.82 and -2.24, so that's been plotted, and I've used little green circles around those points so that you're clear that those are indeed points of inflection. The next thing I've done is try to take into account the concavity. We know that the function is concave downwards from 1.18 to 2.82, so I've drawn that in. I know that the function is concave upwards in two different intervals. The first one is from 2.82 to infinity, so I've drawn that one in, and then also from negative infinity to 1.18, and I've drawn that in. I should apologize. It looks to be concave downwards the way I've drawn it, but it's meant to be concave upwards in that portion of the curve. Now, if you remember, we kind of bypassed the information about increasing and decreasing. What I'm going to do now is take a look at this completed sketch of my curve and see if it adheres to the rules regarding increasing and decreasing that I had previously worked out. My function is supposed to go essentially from decreasing to increasing to decreasing back to increasing if you look at the work we had done previously. And that is the case when I look at my sketch. So this is complete, and this is the level of work that's expected when you do a curve sketching problem. It should be noted that when you're asked to do a question like this on a test or an exam or even on a quiz, you will only be expected to complete one of these questions in the allotted time. To ask 2 or 3 questions is totally unfair because there's just takes so much time just to complete one particular question.